Next, we have Wenzhen talking about robotic touch.
Okay, thank you. It's a great honor to have this chance to speak here as the youngest speaker today. Yeah, actually the second mostly graduated student from test group. So we have been working on something very different from the previous speakers, as you can see from this page. So we're using a robot. So all of my journey starts in 2012. I was just graduated from, got my undergrad degree, and I came to the test office asking for a PhD opportunity. So TED showed me this very cool sensor, the portable gel site built by Kimo. And he said, look, this is a cool sensor. So my plan is that to install the sensor on a robot, and we want to make the robot very smart. For example, can we make the robot do the thing like buttoning a shirt or flipping a page in a book? I said that, wow, this sounds really cool. I'm inside that. So, but very soon I noticed that, what is the gap here? So there's a Chinese word saying like, 1,000 mountains and 10,000 rivers. This is what is between the gel site prototype and the things we can make on a robot and make robot smart. So it's definitely hard, but I can say that after my 6 years of PhD life and 3 years of faculty life at Carnegie Mellon, we have been making some progress. I would say that we are here, but we are on our way. So the first turning point happens in 2014, so led by our lab mates, Ray and the collaborator of Platts from Northeastern. So we built our first prototype of gel site that is small enough and can be installed on a robot gripper. So we firstly showed the demos of a robot test. To the community of robot tactile sensing community. Because before gel site, this is what we typically see a tactile sensor for. You can see that touch sensor can provide information about like the contact, the distribution of the normal force, so it can help you to, like for example, not crash the egg. But with gel site, you can do much more. For example, you can touch the clothes, and you can see so much details about like different textures of different type of fabrics, and also like how this like soft and deformable clothing materials may deform during the gripper. And this kind of rich information definitely tells a lot about like not only what kind of clothes, what kind of material it is, also much more beneath this. So we asked about these questions for many years. So since there are so rich information here, so much more information about the contact surface, how can that help robot with perception? How can it help robots to get a much deeper understanding of the physical world, which is not available before because we have this nice sensor. So to do this, we look back into the human process. I will show this example like Ted like a lot of human touching an avocado. So we can learn a lot from this simple process, such as, hey, this is avocados. We have this special texture that's straightforward. So we're holding this avocado safely, and we know that this avocado is ready to eat or not because we can feel the hardness of it. So that means like the basic thing happens is actually the physical interaction between the objects and the fingertip that's touching it. So specifically, if you look at what is the fingertip of human is like, so it's actually a soft tissue structure that is wrapped around a rigid bone. And during the touch, this physical interaction between the finger and the external objects, there's lots of interesting things happening, both on the external objects and as well as this soft fingertip of human. And most typically, it might get compressed or the skin got stretched. So that is all very relevant to like what kind of physical interaction it is and what kind of information can we perceive or learn from the physical world. So let's think about like this hardness question. For example, like how can we tell the hardness of an avocado? So we started the simplest task. We press the gel set towards a hemispherical shaped objects. So this is actually a piece of silicon I casted. And this is what we can see as the output from gel set. So you can see that this is a very beautiful round shape areas that is expanding. So that tells us like the sensor is in contact with some hemispherical shape objects, and the contact area is growing larger and larger as we press harder. And we can also try to press on another object that is made of exactly the same shape, but of another material that is much softer. And this is the data we can see at this time. So it's still a round area, but the color is much dimmer than the previous one. Why? So because this material itself is softer, during the press, it's not only the sensor deform, the object may also deform. And the softer the object is, the more deformation it generates. So that will make the surface geometry to be much more flattened. And what we see from the color, from the reflection here, actually tells a lot about like what exactly is the shape and how much the shape deforms during this press process. And that is closely related to the physical property of the objects, that is the hardness of it. So in other words, in this process, we can see that the physics of the touch, the physics of the objects, the physics of the finger, or the fingers of the robots, and the interaction between them, that makes the foundation of the perception. But if we look from the perspective of a robotist or engineer, so we try to find a connection between them in a way that we can describe that robot can understand or computer can understand. That means like we need to build a model of ourselves to describe this physics and bridge that into the perception we have. So how to describe this model, how to build this model might be a practical challenge. So for example, if we think back about this hardness challenge about estimating the hardness of the objects, so we know that the physics is that like during the contact, the soft objects may have more deformation and the force may change. But how can we do the model? How can we describe this change numerically? So this is a very challenging task. So since we don't know the solution, we turn to the solution of everything, deep neural network. So this is the network structure we build at the moment, at that point. So we get an input as a sequence of gel set image. And for each frame, we firstly get that input through a convolutional neural network, which tells about spatial resolution. So in this particular case, it tells about the shape of the object at this moment and the contact force. And after that, the information flows into a recurrent neural network, which tells about the temporal information, is how this information changes as the time goes. And finally, although we don't know what happens inside, but it magically generates a number that tells about hardness level of the objects. So that is one example about like how can we model the physics and get some perception. So we look at this example again, like grasping an avocado. So we notice that the second important thing happening here is that this human is extremely capable of successfully grasping these objects without dropping it. So why can human do this? Why can human detect whether the grasp is successful or not so easily? So there actually have been some human studies about like what happens during this tactile process when we do the grasping. So one example of those researchers here. So those researchers look into like the fine deformation of the skin on the fingertip during a slip process, that where the object is sliding away from the fingertip. We figured out that like during the sleeping phase, so there is usually start with like some sticky areas on the fingertips, such as circled by the red circles, and some non-sticky areas that means sleep areas that is in the peripheral areas of the fingertip. So we asked the question whether we can make gel set to do similar things. So we asked the gel set to grasp some objects with a flat surface, like a box here. So when there is a small load, we can see this is what we detect from the motion field, 2D motion field of the soft surface of the sensors, as shown in the first window. Or the things may change if the load is much larger. So you can see those arrows has much larger magnitude. But on the other hand, the distribution also changes. So this shows like what's the magnitude distribution of those markers. So in other words, it's like planar deformations of the elastomer will change if we have larger and larger shear force and finally slip occurs. So at first you can see that everything is very uniformly. So that means like the entire surface is kind of stick to the object surface. But when the force is much larger, so you can see that there's a large redder areas in the middle and very green area in the peripheral areas. So that means part of this soft surface is still stuck to the object surface and part of them has moved. Or in other words, this soft surface has been stretched. And that means like this grass is likely to be unstable and the objects may fail from your hand very soon. So you may ask, like, what happens if we are trying to grasp an object that is kind of small, where you don't have a large area to tell you, like, where is the sticky area, not sticky area. So try to take a look at what happens at this point. So at this area, in this case, the contact area is very small. So you can see there's a small round area and small edge when we ask the robot to grasp a small dog here. So to make things clear, I zoom in to take a look at these very small windows, which shows the geometry of the objects that is during the contact. Or those black markers, they're actually painted on the surface. So they're glued, they're always glued on the soft surface of the sensor. So we can wait for a little bit and take a look at this small window again. So at this time, we may find that the geometry has moved for several tens of pixels, while the markers didn't move a lot. So what does this mean? So this means there has been some relative displacement between these objects in contact and the soft surface of the sensor. And that exactly means the definition of slip. And that means like this object is already sliding along your finger surface for a little bit, and very likely it will drop down. So in another case, if we ask a robot to grasp something very long and thin, so we may see this rich texture again, and after a little while, instead of a translational slip, we may find that geometry has rotated for significant angles. So this is another kind of failure we typically see, which we call them like rotational slip. So recently, we're also looking into some other perception examples, which is more relevant to indirect perception. So we try to look at like how can we perceive the liquid in a bottle. So we take an example of motion of humans. So we ask a human to do a simple shaking that is introducing some perturbations of this entire bottle. So you can see that this simple perturbation will cause the liquid to have lots of vibration. But this vibration pattern may be different a lot according to the type of the water or the amount of the water. So for example, if the detergent, if we compare the detergent and the water, the first one is very sticky, so the vibration magnitude is much smaller and it dies out very quickly. So, and this kind of vibration actually can be perceived by tactile sensing as well, as far as you have a good sensor like gel side. So we do. So we make a robot do the same thing, grasp a bottle to move it from one location to the other location, introduce some perturbations. And this is what we get from the gel side. And if we reduce the dimensionality of the data and draw a 2D data, so it actually makes a very beautiful pattern and very close to a second order damping signal. So in other words, if we fit the models, we can make these signals to be very simplified, to be described by two parameters. One is the decay rate, and one is the frequency of the signal. And that could be different a lot according to what kind of liquid is there in the bottle and the way you shake it. So here, again, we do a comparison between those three different liquids, and they have very different decay rate and frequency after these perturbations. And if we draw those data points in this 2D plot regarding to the decay rate and frequencies, so you can see that the data cluster very clearly. So that makes us easily get a classification accuracy of 100%. On the other hand, you may also see that this data has a distribution along an axis, right? So you may ask why. This is because the data we got are of different volume of water in the bottle, volume of liquid in the bottle. And this frequency of this signal is actually linear relevant to the volume of liquid in the bottle. So we found that this might show that there's some better correlation between that. So to get some finer information, we turn to a more challenging task. So get some sugar solution instead of three distinctly different signals, liquids. And now it's like a bunch of sugar in the water, but with different concentration level. So we try to shake them again and get some data, not very differentiable for human eyes, but still can be seen very differently if we try to calculate the decay rate and frequency. And they fell very nicely onto two planes if we're trying to measure either the height of the liquid or the sugar concentration level of the solution, which is linearly relevant to the viscosity of the liquid. Okay, so that's some examples about what we try to do in different ways to understand like the physics between the contact and the external objects, and how can we turn that into a perception for a robot. So as a quick conclusion here, again, thanks Ted for all the wonderful ideas, helping and the magics to make all the things happen. So again, I think this is a very exciting field. Although it's 1,000 mountains and 10,000 rivers, we are here, but we are heading forward, and we are on our way. Thank you.
Questions?
So that's a very good question. So in many cases, the property of the material of the gel site will have an influence about like the sensitivity level of the things you want to measure. So I will take the example of the hardness measurement. So as I make in the demos, the physics or the foundations of the way we can estimate the hardness is based on like relative deformation between the gel pad and the objects. So in other words, actually the sensitivity range of the measurement objects is in the range that's kind of close to the hardness level of the gel pad. If we're using a harder materials, it might make a better work by measuring the harder objects, and if we use softer materials, it's more sensitive to softer objects.
Great, thanks. Thanks, Wenzhen. Next, we have Ruth talking about everything.